Okay, there is I wrote this blog post about falling space elevators, and a lot of people are like, well, how'd you do that? So let's go over how I did that. And I'm going to do this in two parts. In this first part, I'm going to reproduce the code that I had for the animation in the Wired post. And I'll include the link down below to my Wired post. So let's just get started. What I'm going to do is to model, the way I'm going to model the space elevator is having a rotating Earth, and then I'll have a bunch of balls connected together that start with the same angular velocity as though they were in a cable, but they're not actually connected together. So the whole thing just disintegrated. Okay, there's nothing connecting between them. It's easier to model. And then afterwards, what I want to do is to model what happens if these are connected together, which is a little bit more difficult. So the main idea of a space elevator is to have a cable connected to some mass up here. And if this station mass is above the equator and the angular velocity of this is the same as the angular velocity as the Earth, then that's the geostationary orbit, and so that will stay in the same position relative to the Earth, and then you can have a cable running down from it. You actually have to have the station a little bit further away than geostationary so that the cable actually pulls on it. But right now, I'm just going to make these aren't really connecting in anyway, so I'm just going to have that at the geostationary orbit. So let's find that first. Let's model a geostation. Actually, let me do this first. Let's make the Earth and make the Earth rotate. Okay, so in Python, the key thing is, what's this angular velocity omega? So omega is going to be 2 pi radians per day. That's how fast it rotates, which is actually not true. It actually rotates a little bit less than 2 pi radians because that's the time for the sun to get back in the same position, but I'm going to use this anyway. So we're going to need this in radians per second. So I'm going to say that's, I multiply by this, 1 day is 24 hours, and then 24 hours is 3,600 seconds. So from that, I can get omega. So I want to get omega. I'm going to make the Earth as a sphere in GlowScript vPython, and I want to make it rotate. Now, the first thing I'm going to need to do is to actually rotate the Earth. I want to make it look realistic. So in vPython, this is the z-axis, but when you draw an Earth, it has the poles like that. So I'm going to have to rotate it this way and then rotate it around that axis. So let's make a rotating Earth, and then I'll come back and we'll calculate where this should be and how fast it should be going, and then I'll put the balls in there for the cable, and then we'll let it go. Okay, switching to Python. Okay, here we are in Python. So like I said, I'm going to give you the code. Let's make the Earth. So the first thing I need is I want to use the actual radius and the mass of the Earth. So let's put some constants in here. I'm going to need g. G is 6.67 times 10 to the negative 11th. I need the radius of the Earth, RE. I'm going to call it 6.371 times 10 to the 6th. I need the mass of the Earth. ME is 5.97972 times 10 to the 24th. And then omega. So let's calculate that. Omega equals 2 times pi divided by 24 times 3,600. And let's just print that. Make sure we have a reasonable value. Okay, so that is that correct? Let me check. Yeah, that's good. That's right. Okay, so I have that. Now let's make the Earth. So I'm going to do it like this. This is really great in Python. Earth equals sphere. Sphere is a built-in object in GlowScript vPython. I'm going to put it at the origin position equals vector 0, 0, 0. The radius is going to be RE. And then the color, I'm going to actually use texture equals textures.earth. And let's run that. And there you go. Check that out. There's your Earth. And that's one of the things I love about GlowScript Python. We can make this Earth really simple. But now I need to rotate that. So when we can rotate objects in GlowScript Python, to rotate an object, what you do is you say, let's see, Earth dot rotate. And now I give it the axis about which I want to rotate it, and the angle about which I want to rotate it, and the origin about what I want to rotate. So I want to rotate it about its center. So I'll say origin equals vector 0, 0, 0. What axis do I want to rotate it about? Well, I want to rotate it this way. So I'm going to rotate it about the x-axis. So the axis is going to be equal to vector 1, 0, 0. That's the x-axis. And then how far do I want to rotate it? I want to rotate it pi over 2, which is 90 degrees. So angle equals pi over 2. And let's see what happens. Okay, so I rotated it. Now we're looking at it from the North Pole. Let's call this Space Elevator 1 cable fall 1. Okay, so there I have my Earth. I'm ready to rotate it. So let's do this. I need to pick a time step. So I'm going to say t equals 0 and dt equals 10 seconds, which seems super small for rotating Earth, but I don't know. Let me also say 1 hour, so this is called hour equals 3600. So now I can say while t is less than, let's say 6 hours. See how I do that? Then rate, let's say 100. That's gonna be too slow. Let's do 3 hours. Okay. And now what I want to do is to rotate the Earth. So I know the angular velocity omega. I need to, let's go up here and give an initial angle theta equals 0. That's the angular position of the Earth. Now what I want to do, I don't even need that. So I want to rotate it an amount d theta, right, each second. So I can say omega times delta t is going to rotate the Earth. So let's go down here and do the same kind of rotate function. So I'm going to say Earth.rotate. Rotate. Origin is still the same. Vector 0, 0, 0. The axis is now going to be the z-axis. I want to rotate about the z-axis. Is that right? Yep. So axis is going to be equal to vector 0, 0, 1. I'm rotating about this axis coming in and out of the paper. And then the angle is going to be omega times dt, right? So that is my change in theta. So that's how much it rotates by. I'm going to rotate it that much. That's it. Now I just need to update time. T equals t plus dt, and I should get a rotating Earth. I mean, that's pretty cool. It's a little slow. Let's speed that up a little bit. Let's say 400. And let's change it to 6. I mean, right there, we've got an accomplishment. And now, I will say one thing, and that is that the lighting is wrong. If you want to fix the lighting, it is possible to fix. The default lighting source for Python, I think there's actually 2 light sources out really far away, and you can change that to 1. You can also change the reflectivity of the Earth and all that stuff. I'm not worried about the lighting right now, so I'm not going to worry about that. But I have a rotating Earth. Okay, so now I want a space station, the station or whatever. Let's just call it anything. Let's call it, what did I call it before? I called it B. That's fine. Let's just call it station. I'm going to make a station. I'm going to put it in geostationary orbit, and then I'm going to add the cable. So let's go back and calculate, go back to paper and calculate this geostationary orbit. So here is my Earth, and here is my satellite. And I'm going to calculate this RS. That's the distance for a geostationary orbit. There's one force acting on this, and that's the gravitational force. So if I look at that object, it's going to have a gravitational force pulling that way, and it's going to have an acceleration that way also, if it's moving in a circle, such that I can say the gravitational force is Fg, the magnitude, G, mass of the Earth, mass of the satellite over rs squared. That's the gravitational force on this. And that's going to be equal to ma, where a is acceleration. But it's moving in a circle. The acceleration of an object moving in a circle, this is ms, is going to be ms omega squared times rs. That's the angular acceleration for an object moving in a circle. Now I want to solve for rs. So if I multiply both sides by r squared and divide by all this stuff, I get rs cubed equals g, the mass of the station cancels, mass of the Earth over omega squared. And then I take the cube root. Is that right? Do I really take the cube root? Yep. So rs is going to be g mass of the Earth over omega squared to the 1/3. So I can calculate that distance. Now, I do need something else, right? I need the velocity. What I'm going to do is to use the momentum principle to model the motion of this. So I'm going to say F net as a vector is delta p over delta t. And then where p is momentum, mass, and velocity. And that's going to be p2 minus, that's a vector, minus p1 over delta t. So this says that if I break this into a small time step, which I did, then I can calculate the force, which is only going to be the gravitational force. And if I know the momentum at the beginning of that time interval, I can find the momentum at the end. P2 equals P1 plus F delta t, where that's F net. But I need to know the starting momentum, vector. Well, I already know the angular. If it start with my station on the x-axis, I know it's moving that way, and its velocity is going to be omega times rs times the vector 0, 1, 0. So it's going to be up. I can find the magnitude of the velocity is omega times r, and then I make it a vector. So then I can find the momentum. Once I have this momentum, I can also use the definition of average velocity to find the new position. R2 equals R1 plus P2 over M delta T. So this says that's the average velocity, and I'm actually using it at the end of the time interval. I can find the new position, and then I can just keep doing this over and over and over again. And so what I should get is a geostationary or a satellite orbiting the Earth, staying over the same position. Okay, so let's add this to Python. Switching back to Python. Okay, so here we are. I got my Earth. Let's just go ahead and add my station. I'm going to say station equals sphere. I need to calculate RS. So I'm going to say RS equals, and this is exactly what I said, right? I'm just going to type my equation. It's going to be G times ME divided by omega squared. All of that to the 1/3 power. So I'm going to put my sphere right there. So the position is going to be equal to vector RS 0, 0. The radius, I'm not going to make this a real radius. If really it'd be so tiny you couldn't even see it. Let's put this at RE divided by 20. That might be too small. And then I'm going to make it color equals color.yellow. Let's also have it leave a trail. Make trail equals true. Okay, so that's just a station. I'm just going to run that to see what that looks like. And good thing I did. RE color equals color.yellow. Radius. Oh, did I not put an equal sign? Radius, I didn't. Equals. Okay, so there's my station right there. Let's make it a little bit bigger. 15. Okay. And so the Earth's rotating, and that's not moving, and that's fine. I do need a mass of the station. Let's say station dot m is the mass. And let's say, so the Earth has a mass of 5 times 10 to the 24th. Let's just do 1 times 10 to the 10th. I don't know. I just picked a mass. Now I need the momentum. So station dot p equals omega times rs times the vector times station dot m times the vector 0, 1, 0. Right, so now it'll be moving in the positive y direction. Okay, so now down here, now I'm doing one trick that is partially useful, and that's that the Earth is at the origin. So the position of the satellite, position of the station is equal to the value of r when I calculate the gravitational force. Now I need to use the vector version of the gravitational force. So let me just do that. So let's say that rotates the Earth. F equals negative g times me times station dot m times norm station dot pos. So station dot pos is r. That's the position of that station, and it's a vector. And the norm, I'll show you why, divided by mag station dot pos squared. So mag station dot pos is the magnitude of that vector r, and I have to find the magnitude to square it. But when I do that, my whole force is a scalar value, but I need a vector value. So norm is a unit vector in the direction of the vector r. So that is pointing away, and then the negative sign makes it point back towards there. Now I can update the momentum of the station. Station dot p equals station dot p plus f times dt. Now I can update the position. Station dot pos plus station dot p times dt divided by station dot m. So that's that average velocity. And I think that should work. I think this, so we should have the Earth rotating and the station rotating at the same angular velocity. Let's see, I should probably save it. Save and run. There we go. Oh, is it staying over? Yeah. Okay. That's working. Okay, good. And it ran for 6 hours, which is a quarter of the way around. Everything looks great. Okay, so now what I want to do is to add a whole bunch of masses. And in fact, I'm going to get rid of the station. Let's get rid of this. I'm just going to delete it. I'll leave it there. Instead of one station, I'm going to have a whole bunch of masses. So let's get rid of this. Let's get rid of this. Let's get rid of that. So now it's just the Earth again. So I'm going to do this. N equals 0. And B equals an empty list. So instead, oh, not 0. Let's make this 10. So instead of finding a whole bunch of masses, I'm going to add a bunch of masses to this list. And each of these masses is going to be like part of the cable. And then the station is just going to be the last element in the cable. So what I want to do, let's start, where am I going to start my cable? Let's start it at the Earth. So I'm going to say r start is equal to earth.pos, which is 0. I shouldn't even need to do that, plus vector re0, 0. So my starting location is on the Earth. Now I need to find the length of my cable. What's the total length of my cable? So let's just call that L. It's going to be equal to, isn't it just r start? R start. Minus, no, I don't want to go to the Earth. So minus RE, right? So r start is what, oh wait, that's RS. I call it RS. RS minus RE. So think about where that final station is and subtract off the radius here. That's the space I need to cover. Now, how many pieces do I need? Well, if I have a length L and I want to break it into 10 pieces, 10 stations, then the space between each station would be DL equals L divided by N minus 1, right? Because I'm going to have 9 connecting pieces. Because the first piece is going to be on the Earth. The last piece is going to be not having a connection to it. So I have one less connection. So that's the space between each piece. Okay, I think we're ready. So now I can say this. For I in range N. And I'm just going to say print I, just so you see how it works. So what this is going to do, it's going to go through the range of 10, and it's going to print a number. And that way, that's my little indice that I can use. So you see there it is, 0 through 9. Those are my 10 pieces. Okay, so that worked. If you're not familiar with lists. Okay, so what I want to do is to make a sphere and add it to that list. So I'm going to say B equals B plus a sphere. A sphere. And the position of the sphere is going to be equal to R start plus vector I times dl 0, 0. So the first piece, I is going to be equal to 0. So 0 times dl, it's going to, the first piece is going to be on the Earth. Does that make sense? And then the next time it goes through, I will be equal to 1. So I have dl, and then it'll be 2dl, then 3dl, and so forth. Okay, now I do need a radius. So let's say radius equals r divided by 20, re. What else do I need? I can give it a color. Color equals color.yellow. I'm going to also do this. P equals vector 0, 0, 0. So I'm going to give it a momentum. I'm not going to have a value in there. And then I'm also going to say M equals M station divided by N. M total. Let's call this M total. Okay, so I don't have M total. I deleted that. So let's go up here and say M total equals 10 to the 10th. Okay, so those don't have any values that make sense. Well, that one does. Momentum doesn't, but I'm gonna fix that. Okay, so let's just run this. This is that little code right there is gonna go through and make all those things. They're not gonna be animated, but they're gonna be made. There you go. So I have 10 pieces of my cable right there. I can change that into whatever I want. Okay, now I need to go through and set the momentum. Now for the momentum, remember, I want them to start with not in orbit. I want them to start with the same angular velocity. So they're all going to have the velocity of omega times r, where r is going to be their position. So let's do this. For P in B, let me just show how this works. Print P.pos. So it's going to go through each one of those elements in that list and call it P. So I can print the position of all of them like this. That's their positions. Okay. So, but I don't want to do that. I want to say P.P, the momentum of it, is going to be P.M, the mass, times vector 0. I want them moving in the y direction. Omega times r, but r is going to be P.POS 0. I think that should work. No, that won't work because P.POS is that's a vector. So mag, let's do mag right there. Okay, because the position vector is this way, but I want it moving that way. There's another way I could do it with the cross product, but I think that's fine. Okay, so that will set the momentum for each of those things. Each of them is going to have a different force on it, so I need to calculate that. So let's say make another list, F equals an empty list. And I need to put some values in there. So I'm going to say for I in range N, F equals empty list. Okay. Now I can go through, F equals F plus vector 0, 0, 0. So now they all have a vector value even though it's 0, and I can set it in my loop. Okay, so now down here, I calculated the force on that station, but I actually want to calculate the force on all of them. So I'm going to say for Fs in F, which is a little weird, I am going to, let's see, is that what I'm doing? Yep. Fs in S, Fs equals negative, I can't do that. Let's do this. For I in range N. See, I have to do it this way because I need to use a number, because I'm going to use the corresponding element in a different list. So Fi is going to be equal to negative G times Me times B dot Bi dot M. That's the mass of the 0th element, if I'm on the first one, times norm Bi dot POS divided by mag Bi dot POS squared. So that's going to calculate the force on each element. Okay, now let's go through. I can go ahead and update the momentum. I can do this all in the same thing. So Bi dot P equals Bi dot P plus Fi times dt. See, I'm doing it for all of the pieces. Bi dot POS equals Bi dot POS plus Bi dot P times dt divided by Bi dot M. And I think that will do it, right? Because then I go through and calculate the force in every piece. I update the momentum, I update the position, and then I update time. It should work. Let's just see if it does indeed do what we expect. Oh, okay, one thing. I know one thing. Okay, one thing that happened was a mass fell through the center of the Earth and exploded. So let's do this. Let's say what do we do if a mass hits the Earth? So I'm going to put in here if if mag of Bi dot POS is less than, let's see how I did it before, if is less than Re, then I want to stop it. I want to stop it, make it sit on the Earth. So what I'm going to do is to say its position, Bi dot POS, is going to be equal to the surface of the Earth. So I'm going to write that as radius of the Earth times, so if it's less than the surface of the Earth, I'm going to put it back on the Earth. So it's going to be that times norm Bi dot POS. Right, because if it's rotated, I need that vector location. I can't just say it's not on the x-axis anymore. And then I'm going to set the momentum of that Bi dot P equal to the angular velocity of the Earth times the radius. So it's going to be equal to, and in this case, I do need to do a little trick. It's going to be the cross product of Bi dot POS and the vector 0, 0, negative omega. So this is R cross omega gives me the velocity. I think it's omega cross R, but that's fine. This is going to work. That's the way I did it before. That's the cross product, and then I have to multiply it by the mass, Bi dot M. So if it hits the Earth, then I put it back on the Earth, and I give it a momentum pointing in the direction of the Earth, and I think that should prevent it from blowing up. Let's just see. Something happened. Bi cross, Bi. Too many right parentheses. I can fix that. Okay, too many right parentheses. Too many right parentheses. So cross Bi, this should not be right parentheses right there. There you go. And so here's the cool thing. Let's make this, let's change this to 100 pieces, because if you can do 10, you can do 100. And let's make the radius a little bit smaller so you can, bigger so you can see it, 15. There you go. I like that. Okay. Now, you'll notice something cool. The first pieces, they fall and they hit, right? But if they get up too high, then they don't hit because their orbital velocity prevents them from hitting the surface of the Earth. Now, this is in the case where the pieces of the cable are not connected together. So that top piece is just a station. You can make it bigger if you want to. But what happens if they are connected? What they're pulling down on it, and it's going to be a different effect. I mean, it's the same kind of thing, but it's going to be different. That's much more much more complicated to calculate. So I'll do that in another video. That's the same animation I had in the blog post, and I hope that helps. I'll give you the code down below, I'll put a link to the blog post down below, and I'll talk to you later.